the slides from Ayush, so I'm sending out the thesis, the reviews, and the slides to all members of the committee.
Thank you. Thank you.
And I see Ivo Petraš has joined. Ivo, hi. Can you hear us? See us? Ivo is, where is Ivo?
Yeah, and it seems that the YouTube live stream is already up.
Okay, thanks a lot.
Can you hear me? Hi, everybody.
Yes, we can hear you, we can see you. How are you in Košice? Everything okay?
Yes, everything okay, thank you. And in Bratislava?
Yeah. Perfect.
Good.
So is this also your first public PhD online meeting?
Yes, the first time.
You will be the first from your university, probably, no?
Yes, I will know how to do it, and we can do it in our university as well.
And better, yes, as usual in Košice.
We will see.
Yeah, our head of the pedagogical department is also here. She's sitting with Michal to see how everything works. Yeah.
Yeah. Tak je to úplne verejné.
So, Michal, who is still missing?
Ale bude tam aj záznam. Bude tam aj záznam na dosmrtne. To tam určite bude tak dlho.
Potom už to nemusí byť.
Okay. Však bude celkový záznam, takže všetko bude.
Toto sa mi páči, že ste to dali aj na YouTube.
Ano.
Ináč, keď neviem, či by to bolo možné.
Positive feedback.
What was it, Alois? Was it your vacuum cleaner or something like that?
I can tell you honestly, the coffee maker.
Okay.
I'm making a coffee because I expect a long discussion, and,
yes. I will
and this is the time for my coffee. Yeah. Sorry.
I will send the secretary to everybody everywhere to give you a coffee. I will at least.
That would be too kind.
No, this is my time for coffee, but no problem. I am sorry I cannot offer you coffee there, but maybe you have the same situation, possibility.
And Jan, you are also maybe more experienced. So how do you handle the final part of the thesis with champagne? That I don't know still with the online meeting.
You mean the proclamation?
When there is a champagne and everybody.
Well, we have the principle BYO, bring your own
bottle. Yeah, please.
Yes, bring your own bottle. Yeah. But I heard the suggestion of the colleague. Do I still have time to go and get the coffee myself, or is it too late?
We still have some time, yes.
Okay, it will not take longer than 1 minute. Huh?
Yeah. Okay, so coffee time for everybody, yeah?
Yep.
Zdravím vás. Hello, everybody. No, dobrý deň, prajem.
So it seems.
Hi, Monika.
Aha.
Everybody is here.
Ako to, že Anka nemá rúško, keď ste dvaja v miestnosti?
Ahoj, Monika.
Anka, rúško nahodiť. Zdravím ťa, ahoj. Dávno som ťa nevidela.
Ale nevidím ti celú hlavu, iba polovicu, neviem prečo.
To je naschvál.
Áno, vyzerá ako horná časť, vyzerá lepšie ako dolná. Dobre, nevedel som.
Hello, Ayush, how are you?
Hello, I'm good, thank you. How are you?
I'm well, thank you.
Okay, I would like to double check with all members of the committee that they have received login information for the Helios voting, which will be done in the private part of the defense. So is there anybody who did not receive the logins?
I have it.
Okay. I have.
I'm looking for, I can tell you honestly, I managed to open my mailbox, but in which, because you have sent to us a lot of many mails, yeah. In which one?
Look for Helios. Helios was sending the email.
Helios, but you were the sender, yes?
No. Helios was sending it. I was just sending mine as an
Helios, okay. Helios, voting administrator.
Exactly.
Right.
And look, we still have time because first we will do the public part of the defense, and then we will have some time to figure out these technical issues.
But we will need it at the end only. No?
Yes.
Not now.
Yes.
Yeah, to the end. Election. So we have to. Take this address, what is election URL, yes? This address?
Yes, exactly.
And election fingerprint is what?
No, you don't have to worry about that. You just click on the link. But let's wait with that until the...
All right, I have my voter ID and my password.
That's exactly what we need, yes.
All right, thank you. Sorry for disturbing.
Okay, and Michal, you will probably explain to the members of
during the private part, I will explain everything. Yeah. So now I will start the official recording of the exam, and I believe it's now about time to start. We have all members of committee logged in. Let me just double check. Yes, everybody seems to be present. So good morning, everyone, again. My name is Michal Kvasnica. I am the chairman of today's examination committee, and together with me are Professor Alena Kozáková as the first reviewer. She is from the Slovak University of Technology in Bratislava. The second reviewer is Professor Jan van Impe from KU Levan. Welcome. Then we have members of committee in alphabetical order, Professor Monika Bakošová from Slovak University of Technology in Bratislava.
Good morning,
Professor,
everybody.
Jozef Markoš, also from the Slovak Technical University.
Good morning.
Professor Alajos Mesáros, also from the Slovak Technical University.
Morning, hi.
Professor Ivo Petráš from Technical University Košice. And Professor Stefan Schlosser, also from the Slovak University of Technology. And the final person present is Professor Miroslav Fikar as the supervisor of Ayush Sharma, who will be defending his PhD thesis today.
Good morning, everybody. Maybe just a little word, if you could turn off your microphones if you not speak, so that there is no noise.
Yeah, good suggestion.
Thank you. So to introduce Ayush Sharma as the student who will be defending the thesis today. Ayush Sharma was born in 1990 in India, where he has received in 2011 his bachelor degree in biotechnology from LP University. And then he moved to Europe, specifically to Italy, where he got the master's degree in food and chemical engineering from the University of Salerno in Italy. And during this master's, he also spent 1 year at the Corvinus University in Budapest in Hungary, where he also got a major in food processing engineering. Then in 2014, Ayush has joined our Department of Process Control at the Faculty of Chemical and Food Technology at the Slovak University of Technology in Bratislava as a PhD student. And currently, Ayush is working as an IT specialist at IBM Slovakia. So that is his brief CV. And today, Ayush will defend his dissertation thesis, which is entitled Mathematical Modeling and Optimal Operation of Membrane Processes. 2 reviews have been obtained for this thesis. Both are positive and they are not raising any significant concerns. Ayush has fulfilled all formal requirements to be able to defend his thesis. Specifically, he has published 4 journal papers, 3 of which are published in the current contents journals, like 1 in Computers and Chemical Engineering and 1 in Journal of Process Control, where he's also the first author. And moreover, he has co-authored 10 conference papers. So I, as chairman of the committee, can confirm that Ayush has fulfilled all the formal requirements and defense can go on. Now I would like to give the word to Professor Fikar as the supervisor to tell us more details about Ayush.
Thank you very much, Michal. Well, you almost said everything I wanted to tell, but I would like to say that Ayush worked on optimal control of membrane processes. He also participated on investigation of fouling mechanisms in membrane processes, the thesis that was done by Martin Jelemensky. He participated in several national research projects from VEGA and APVV agencies. And he also, during first 3 years when he was employed by our university as assistant professor, he was participating at theory of automatic control and industrial information systems, where he got interest in XML processing, and that he is actually doing now at IBM, where he started from 2017, and from that date Ayush was external PhD student of our university. And you said that he's got very nice results with journal publications and also conferences. There are major conferences of International Federation of Automatic Control, IFAC, IEEE, and also ESCAPE papers. And maybe to conclude, the work he done was checked for originality, and the protocol of originality says 3.8%, which is mainly in bibliography. So I could conclude that this work is declared as original. And for me as a supervisor, it was a very nice experience to work with Ayush. He always knew what he wants to do. It was sometimes quite difficult, but I enjoyed this experience, and I am very happy that it took us quite long, Ayush, but we are here, and I am happy for this moment. Thank you. Michal, turn the microphone on.
Sorry, it was my fault. Thank you for the evaluation, Mira. I wanted to ask Professor Schlosser to mute his microphone. We are getting some echo. So just turn off your microphone, please.
I have turned, it is on.
But please turn it off because now Ayush will give the presentation and we are getting some echo. Okay, perfect. Thanks. Thank you very much. I would also like to point out that the thesis was sent out to other partner organizations, and no comments have been obtained in a reasonable time. So I can further confirm that no objections to the thesis or to the defense have been received, and therefore the thesis defense can go on according to the laws of Slovak Republic. Now I would like to give the word to Ayush to tell us in a time frame of 20 minutes about the most important results of his thesis. So Ayush, the floor is yours.
First of all, thank you for everybody for being here, and Mikhal and Miroslav, Professor Fikar, for introducing me. I hope everybody can hear me clearly. So I will take it as a yes, and I will start with the presentation. So again, good morning to everybody. I am Ayush Sharma, and now I'll be presenting my PhD thesis titled Mathematical Modeling and Optimal Operation of Membrane Processes. My supervisor is Professor Miroslav Fikar. Firstly, let's go through the objectives of the thesis. So the first aim was to investigate what are the membrane processes, what is membrane separation technology, what are the different types of membranes, different configurations of this process, and all the research work that has been done on membrane separation technology. Secondly, to model batch membrane processes. So this thesis or this research work was done only on batch membrane processes. So the second step was to model batch membrane processes. Then to use this model into optimal operation theory was the third step. And finally, to validate the optimal control strategy over the laboratory membrane plant was the final step. So from theory of membrane processes to the implementation on the plant was the objective of this thesis, basically. So this is the outline of the presentation. Firstly, we'll go to the motivation, why to use membranes and to control them. Secondly, we will go to batch die filtration. This is a type of membrane process which we'll be dealing with. We will see the description of the process, the model, the optimal control problem to minimize processing cost, the solution to which was found analytically, then the experimental case studies. After that, we will go to another membrane type process, which is batch die filtration, but with partial recycle. We will discuss about the process in detail. Then again, we'll go to the mathematical modeling of this process, followed by the optimal control to minimize the cost. And the solution to this part was found numerically. And finally, we'll move to the conclusions. So firstly, the motivation to use the membranes. There are other techniques in the industry, for example, distillation, with which we can separate some components. The problem with distillation is it needs higher temperatures. The basic concept is based on condensation and evaporation. Most of the biomolecules, for example, proteins, antibodies, they get denatured at higher temperatures. In membrane separation process, we maintain the temperature based on the product we have. So the denaturation or destruction of the molecule doesn't take place. Another technique used widely in the industry is solvent extraction. The first problem here is extra cost for the solvent. Then after the separation step, we have product plus the solvent as a mixture. So we need another separation step to remove the solvent from the product. And still finally, in the end product, we have minute traces of the solvent. In membranes, these problems are not there. Now, to control this was to minimize the processing cost. In this thesis, we deal it via minimizing the processing time, or minimizing the consumption of water, or minimizing the requirement of the pumping power. So let's move on to the first type of membrane process, that is batch die filtration. First, we'll go to the process description. So this is a schematic representation, a basic schematic representation of membrane process. And this is the image of the laboratory plant we have in our facility. So initially, the solution with the components that we want to separate is fed to the feed tank. And then using the pump P1 or feed pump, it goes to the membrane M. Now the membrane allows a part to go through it, that is called permeate, and a part is rejected by the membrane, that is called retentate. So the permeate leaves the system, the retentate returns back to the tank. This is a basic membrane separation process. Now, in order to reduce the concentration of certain components, we can introduce diluent or water from outside using this pump P2. This process or this step makes this whole process batch die filtration. The control input for this batch die filtration is denoted as alpha, which is the ratio of inflow of diluent to the outflow of the permeate flow. Some of the basic modes of alpha are when alpha is 0. That means our inflow of the diluent is 0. Permeate is leaving the system with the flow rate of QP, but there is no inflow of diluent. That means the volume decreases in time and the concentration increases. Another one is when alpha is equal to 1. That is when inflow of diluent is equal to the outflow of the permeate. When inflow is equal to outflow, that means the volume stays constant. And the third one is when alpha is equal to infinity. This is called pure dilution mode because this is an instantaneous step. We stop the process and we, within an instant, add some certain volume of diluent directly to the feed tank to reduce the concentrations. Now, this is the P&ID diagram of the membrane process we have in our facility. The important things to be noted here are the pressure controller, temperature controller, and the membrane. The membrane we used here is a nanofilter membrane for our experiments. The reason is our solutes or components that we wanted to separate were sugar and salt. Specifically, we had lactose as sugar and sodium chloride. So we wanted to separate sugar and salt. Now, for example, if we want to separate fat and proteins, we will use microfilter. So in this case, we use nanofilter and our components were lactose and sugar. Our whole theory, this thesis is dependent on controlled temperature and pressure. So we were using the sensors before and after the membrane for pressure to control the pressure of the system. And we were using the temperature sensors of the retentate side to feed it to the temperature controller to maintain the temperature at a constant value. And the research regarding these basic controllers has been published in this paper mentioned below. Now let's take a look at the process model of batch die filtration. So for our lactose and salt system or salt solution, these are the two ODEs that we have. Finally, C1 is the lactose concentration and C2 represents the salt concentration here in these equations. Alpha is our control input, which is constrained between 0 and infinity, that is non-negative. QP in these equations is, as we discussed before, the permeate flow rate that leaves the system and is generally a function of concentrations. Now the next step, we have the model. Now the next step is to estimate this permeate flow rate as a function of concentrations. So we did experiments and we tried to fit some models to the experimental data. The first model is the basic model, which assumes that the permeate flow rate is only the function of the bigger solute. In our case, between lactose and salt, the bigger solute is lactose. So the permeate flow rate is only a function of C1 here, as we see, the lactose concentration. For comparison, we also estimated another model, which is an extension of limiting flux, denoted as generalized limiting flux model. This also includes the concentration of sodium chloride or salt inside it, second component, C2. So our optimal parameter estimation problem was to find these parameters or to estimate them, and this was published in this paper. And these are the results of the estimation. So we have our parameters estimated. So now we have our model, we have the estimation of the permeate flow model, we can move towards the optimal control of batch die filtration processes. One objective was to minimize the time, as we can see here. Another can be to minimize the diluent or the water consumption that we put from outside. We had an objective that is a weighted function of both. So WT is the weight over the time and WD over the diluent consumption. And this is subject to our ODEs for both concentrations and the constraint over the control input. The solution to this was found analytically using Pontryagin's minimum principle. And in this hook. There are many cases and studies related to this. So finally, using this principle, we found out that for these experiments, the optimal strategy should be a 3-step one. So initially, we will give alpha minimum or maximum, this is 0 or infinity, to reach the so-called singular surface curve, which is this. So until we reach that, we give alpha equals to 0 or infinity, depending on the initial concentration. Then we give the so-called singular alpha to stay on this singular curve. And when we reach certain ratio of final concentrations, we give again minimum or maximum to reach the final concentration. So this is the three-step strategy we used for the experiments for optimal strategies. Now let's go on towards a case study. So the green molecule here are lactose and the red ones are sodium chloride. And using membrane separation for an initial volume of 21 liters, we want to increase lactose concentration from 50 to 110 kilogram per meter cube and reduce the salt concentration from 5.3 to 1 kilogram per meter cube. This case, along with many other cases and experiments, were published in this paper. So these are our 3 experiments that we did. In first one, we did the same case, but with traditional strategy that is currently done in the industry. Then we did 2 time optimal strategies based on the both the models that we estimated. So these were the input strategies. In traditional, it's simple. We first gave alpha minimum to increase lactose concentration. Then we gave alpha equals to 1 to decrease the sodium chloride concentration, and we reach our final concentrations. In case of time optimal strategies, as we discussed, it's a 3-step strategy. Initially, because of the concentration, we need to concentrate lactose with alpha equal to 0. Then we reach the singular curve, and then we give the alpha singular. And once we reach the ratio final concentrations, we do the pure dilution step, that is alpha equals to infinity. So these were the general equations for singular curve and singular alpha, as we saw before. And as these are time optimal strategies, in our multi-objective function, we can plug, or in these equations, we can plug WT1 and WD equals to 0. That are the weights on the respective optimizations. And after these simplifications, these are the 3 experiments or strategies we implemented. So in case of time optimal strategy based on limiting flux model, the alpha singular is equal to 1. And in case of time optimal strategy based on generalized limiting flux model, the alpha singular is 0.91. Now let's see the results of these experiments. So firstly, we did the traditional strategy. The green circle here in the concentration diagram, the first one, represents the initial states or concentrations, and the red circle represents the final concentrations we want to achieve. So initially, alpha is given 0 to increase the lactose to its final concentration while keeping salt constant. Then in the second step, we give alpha equals to 1 to reduce the salt concentration while keeping lactose constant at final concentration. And we reach the final concentration. The second image shows the permeate flow rate data of this experiment. Initially, we can see when the lactose concentration is increasing, the permeate flow rate decreases. And in the second step, when lactose is constant and sodium chloride is decreasing, we see that the permeate flow rate is almost constant, slightly increasing with time. And the time taken for this experiment or to reach our objective was 4.28 hours. The second strategy we implemented was time optimal strategy based on the limiting flux model. So initially, again, we gave alpha equals to 0. That is, we concentrated or over concentrated lactose, as we can see here, to reach the switching concentration or the singular curve equation. Then we gave alpha equals to 1 to stay on the singular curve till we reach the ratio of final concentrations. And at that moment, we stop the process. We know the final volume we need, and we just pour pure dilution step to reach the final concentrations. This experiment or this strategy took 3.85 hours to reach the same objectives. Then we implemented or did experiments with time optimal generalized emitting flux model based strategy. This was similar to the previous one. The only difference is the switching concentration or singular curve is different and the alpha singular is different. So again, we over concentrate lactose in the first step with alpha 0 to reach the switching curve, singular curve, and then we gave the singular control, that is 0.91, to stay on the singular curve till we reach the ratio final concentrations, and then we again do the pure dilution step to reach the final concentrations. So in the result of time, we can see we saved from 10 to 13% of the processing time using these optimal strategies. Now to do some discussion on the batch die filtration research work we did in this thesis. So first of all, it was not straight away that we have the plant and we start the optimal strategy implementation. We first had to set up for experiments. So for example, there are no sensors for concentration measurement. So we had to do many experiments and figure out some models using which we can, using the existing sensors on the plant, somehow figure out at our given sample time the concentrations of both the components. The other issue was to implement the basic controllers. As I said, our theory and our assumptions say that we need to have constant temperature and pressure. Not only for that, but also for maintaining the structure of membrane, we need to control these. So these were set up before, along with the communication with the PC, sensor input-output data. Using MATLAB, we needed to give the inputs to the plant so that we can run our experiments. So this was firstly done in the thesis or in our research. Then we went to the optimal strategy and other experiments. So this was the first time that on membrane process optimal strategy or these kind of strategies were implemented. So we not only implemented time optimal strategy and traditional, but we also implemented several other strategies. For example, we implemented multi-objective cases in which we wanted to minimize both time and diluent. Now this was batch die filtration. Now let's look at the batch die filtration with partial recycle. So what is this partial recycle? We'll see in this process description. So this is a basic membrane process configuration. This is membrane process with partial recycle. The partial recycle is of actually the retentate. So in the second one, we can see the retentate is not only turning to tank, but through a valve, it can also be returned to a recirculation loop. And this recirculation pump then pumps it back to the membrane. So the additional things are this pump, this loop, and this valve. So in batch membrane or batch DS, retentate returns to the feed tank only. But in this partial recycle, it can all be partially or completely recycled to this loop in between. Now, why to use this? First of all, the advantage is because of these two pumps, we always have a defined flow rate and higher cross-flow velocity across the membrane. Now, because a certain amount of volume of solution is always in the loop, we can reduce the tank size and the piping. Now, this configuration is known for overall energy or power reduction. This we will see in our optimal control problem. The only disadvantage is we need to invest more in the cost for the extra pump and the loop and piping. Now, let's move on to the process modeling for this kind of configuration. So for the modeling, we divided the whole process or configuration into two parts. So first we took the feed tank and modeled it. Then we took the loop part and did the mathematical modeling for that. This research has been published in this paper. So with respect to the tank, we ended up with these two equations. The first one represents the dynamics of the volume, and the second one, the concentrations inside the tank. For the loop, we ended up with this equation for the concentrations inside the loop. Now, in this case, we have two control inputs. In batch die filtration, the previous process, we had only alpha, that is between 0 and infinity. But in this case, this is partial recycle or splitting factor is called S, and it can be between 0 and 1. QP is the permeate flow rate, and it's a function of the loop concentrations. Now, R in these equations is called rejection coefficient. What rejection coefficient is a parameter of the membranes. So for example, if R is equals to 0, that means that component is completely allowed to pass through the membrane. And if R is equal to 1, that means that component is completely stopped by the membrane. VL and QL are the loop parameter constants. So these are constant values for the loop. Now let's discuss a bit about this second control input, that is S. We can do this via two basic modes of it. So when S is minimum, that is S equal to 0, In this case, everything returns to, so the whole part of the retentate returns back to the loop and nothing returns to the tank. The opposite scenario is when S is maximum, that is S is equal to 1. In this case, everything returns to the tank and nothing to the loop. And when S is in between 0 and 1, some part of the retentate returns to the tank and some part returns to the loop. Now let's move on towards the optimal control of this configuration. So as I discussed before, this configuration is known for reducing the power required by the pumps. So we did the multi-objective function, that is minimization of time and the power consumption. After some derivations and formulations, we've discovered that to reduce the power, we need to reduce this flow rate coming from pump E1 called Q1. So if we minimize Q1, we will minimize the power or pumping power requirements. So this is an objective problem subject to our ODE for volume and tank concentrations and loop concentrations and the following initial and final constraints. So we have the initial and final constraint on the tank volume, on the initial one on the tank and loop concentrations, the overall mass constraint, and the constraint on the control inputs. So this is a case study again. The green molecules, they represent our product, and the red ones represent the impurity. So using membrane separation, we want to increase the product's concentration from 10 to 100 mole per meter cube and reduce the impurity concentration from 31.5 to 10 mole per meter cube. And the loop parameters are here. The loop flow rate is 0.25 meter cube per hour and the loop volume is 5 liters. The model used for the permeate flow here is the limiting flux model, which we also discussed in the previous configuration, that is batch die filtration. And constant parameters are taken from literature, which are these. The rejection for the product is 1, so product is totally stopped by the membrane, and the impurity is totally allowed to pass through by the membrane, so R2 is 0. So here is our objective problem, and the solution to this was found numerically. As this problem was not affine in our control input, so we couldn't go through with the analytical solution. So we had to move to numerical techniques. So we used orthogonal collocation method using Dynoc toolbox, and we implemented a control vector parameterization method in MATLAB using adjoint gradient method. This research with many cases and modeling has been published in this paper. Now let's see our control input results when we implemented this case study in simulation. So first case was we wanted to do the minimization of time only, so minimum time case. In this case, S was always equal to 1. Alpha was, as we discussed in our analytical solution in the previous configuration, was a 3-step strategy: alpha was 0, then alpha 1, and alpha infinity. S equals to 1, as we discussed before, means everything returns back to the tank and nothing goes to the loop. Then we tried almost minimum time, where we are minimizing time mostly, but we also gave a small weightage to the power consumption. In this case, mostly it was 1, then it moved to 0.8, and then finally for a minute second to 0. Then we had economical optimal scenario. So this is in between both minimizations, and it reduces both the time and the power and minimizes the cost in total. And in this case, we can see S is around 0.25, then 0.1, and then finally 0. So in this case also, we found out that it's 3 steps are enough for the optimization, and if we increase more steps, it will just increase the complexity. And the reduction in the cost was not much. The next was we moved towards almost minimum power, where more weightage is on minimizing the power than on time. And in this case, we can see S is very close to 0. That is, most part of the retentate is returning to the loop. So we can see here, as we move towards almost minimum power, the loop is coming more and more into picture. And when finally we did the minimum power, S was always 0. So every part of the retentate was returning to the loop. Nothing was going back to the tank. So this configuration was totally being used when we were using minimum power scenario. And alpha in all these cases or all these scenarios was exactly like was in the batch die filtration. It was a three-step strategy with 0, 1, and infinity based on the limiting flux model. In the table, we can see these the time and power. They both are opposing objectives. So if we want to minimize the time, we maximize the power, and if we minimize the power, we maximize the time. And so, the economically optimal scenario is a better one if somebody wants to minimize both in order to reduce the cost. Finally, we go to the conclusions. So firstly, we did mathematical modeling, and we did some simplified versions, and also some other forms of models based on the configurations for both batch DF and batch DF with partial recycle of retentate. Then we researched on the optimal operation of both batch DF and also batch DF with partial recycle. In case of batch die filtration, we used analytical technique. And we did experiments to validate the optimal strategy on the laboratory plant. In case of batch D with partial recycle, we use simulation to prove our results. And the major conclusion was that if we want to just minimize time, there's no need for recirculation, and batch DF is enough. But if we want to minimize power, batch process with partial recycle is suggested, as it reduces the power requirements. These are the major journal publications that were published during my thesis. So the first one deals with batch die filtration with partial recycle, which includes the modeling and the optimal operation. The second one deals with the batch die filtration, where we implemented the optimal control strategies over the plant. And the final one is regarding the theory and optimal cooperation of membrane processes, including membrane fouling. Thank you.
Thank you very much, Ayush, for presentation of the results. Now we will move to the reviews of the two reviewers. I suggest that we go ladies first. So I will ask Professor Alena Kozakova to read the most important parts of her review and ask questions.
Okay, thank you. So I will concentrate on the main parts because mostly everything was presented now. So the dissertation deals with optimal operation of membrane processes with the focus on experimental verification of the selected model-based optimal control design strategies applied as batch open loop and closed loop dia filtration configurations. The thesis has 114 pages and is organized in 6 chapters, including introduction and conclusion, and is divided into 2 main parts, theoretical background and thesis contributions. It is well written with minimum typos and grammatical errors. Achieved research results have continuously been published in high quality papers and journals. The list of authors' references include 14 items, 3 out of them being papers in journals indexed in the current contents database. So the methods I can omit. Which achievements and new findings were presented in the dissertation. So here is the list of them, of the achievements. So firstly, modeling of batch membrane diafiltration processes with and without retentate recirculation. Then comparison of both configurations in terms of economic benefits brought about. Next, modification of the optimization task for individual batch configurations. Then optimal operation design of batch diafiltration without recirculation, so-called open loop, and its experimental verification on a laboratory plant using the experimentally estimated filtration models. Next point is optimal operation design of batch diafiltration with recirculation, closed loop, using numerical optimization. It is finding optimal diluent addition rate and recirculation ratio. Comparison of optimization results for both configurations based on case studies and their generalization for specific optimization tasks. The case studies prove the economic benefits from optimal operation compared to classical industrial strategies with no need to modify existing industrial hardware and software setups, which are contribution to the further development of science and technology. The dissertation is a contribution to the long-term research in optimal control of batch membrane processes carried out at the workplace. Besides modeling different configurations and their comparison in terms of economic measures, its main asset is the verification of theoretical results in laboratory conditions for selected case studies. The contributions to further development of the field comprise modeling of batch membrane processes configurations with and without recirculation and their comparison in terms of economic benefits, modeling of filtration rates based on experimental data using dynamic optimization problem for finding optimal parameters of filtration models, development of optimal operation of batch open loop diafiltration using Podtyagin's minimum principle, its experimental verification based on experimental filtration models. Then, for batch closed loop configuration, specification of optimal diluent addition rate and recirculation ratio using numerical optimization. And finally, verification of developed approaches on case studies for both batch configurations, generalization of obtained results. As for fulfillment of dissertation objectives, the main objective of the dissertation was to study theory on mathematical modeling and optimal control of batch diafiltration processes and to verify selected issues experimentally in laboratory conditions. This included, first, study of batch closed-loop diafiltration processes, their mathematical modeling, numerical optimization, and solution of case studies. Second, study of optimal operation strategies for batch open-loop diafiltration processes and their implementation and verification on a laboratory membrane plant. The thesis objectives were fully met. The achieved results are described and demonstrated on 3 case studies implemented on the real plant and 3 case studies taken from literature. Then I have minor comments and questions. So may I ask now the questions?
Yes, sure. Go ahead, please.
Okay, so these are some formal problems. So my first question is, could you please closer clarify the choice of weighting coefficients delta in equation 4.17a based on experimentally observed variances? So how did you choose the weighting coefficient delta in equation 4.17? Or should I read all the questions maybe?
I suggest to go one by one, otherwise we will get lost.
Please.
Ayush, you have to unmute yourself first.
Hello, thank you for the review.
Mm-hmm.
So, can you see my screen?
Not yet.
Stop sharing, start again.
So I suggest that you turn off the presentation mode and then you turn it on again.
So can you see now?
It's coming up. I can see it.
Okay, thank you. Yeah, so the question is basically regarding this equation, that is the dynamic problem for the parameter estimation. And specifically it's regarding these the denominators we have in these equations. So this is basically standard deviation, and because our measurement data was not huge and it was of varying quality, So if we have this variance in the denominator for each optimized parameter for the state, it gives a better solution. That's why we.
Okay. Okay, thank you. My next question is in equation 4.4.1, you declare that, time minimization results in reduction of costs by decreasing the consumption of electric energy and labor costs. Okay, so it's a kind of philosophical question, whether time minimization really results in reduction of costs. Is it true in general?
Well, in general, I would say it's not true always, because time minimization may result in some extra implementation of hardware, or maybe software, or maybe manual work. In general, I won't say it's true, but in our thesis or research, it's based on that we will not implement anything extra on the existing industrial setup. So we won't need any extra hardware or software and manual work. So only for this particular case, it will result in the minimum cost via these means.
Okay, thank you. And my last question is whether there are any recommendations for choosing weighting coefficients in equation 5.22a for almost minimum time and power scenarios. Why is the minimum diluent term always 0 in the proposed scenarios, except for the scenario number 6 on page 87?
Thank you for the question. This was a very good point, because I could have included more cases in the thesis. So when we were doing the research and the simulation studies, we discovered that the diluent and power minimization scenarios are equivalent. So if we minimize the power, we also minimize the diluent. So just for the showing purpose, I included the diluent as a one case in the last mode. But actually, if we minimize the power, we also minimize the diluent.
Okay, that's it. Yes, thank you. So my overall assessment: the submitted dissertation thesis fulfills the requirements specified in the Act number 131/2002 and study regulations of the Slovak Technical University in Bratislava and the Directive number 5/2006N. Therefore, I recommend to accept it for the defense, and after a successful defense, I recommend to award Mr. Sharma the degree Philosophy Doctor.
Thank you very much, Professor Kozakova, for the review. And now we would move to the second reviewer, who is Professor Jan van Impe from KU Leuven. Jan, are you still with us?
Yes, I'm trying to switch on my microphone and, if possible, the video. Let me see. Allow. Yes, of course, I allow. So does this work now? You can see me and you can hear me?
I can only hear you. I cannot see anything because it's still Ayush who is presenting.
Okay, I will stop sharing then.
Yeah, please do. Now, Jan, if you want to share your screen, you can.
It's okay. But you can see me in the video, right? Okay.
Yes.
So, of course, I'm less familiar with the procedures you have in place at the Technical University in Bratislava, but of course, I agree with all that has been said in the previous report, although I did not see it myself beforehand, of course not. I can state a bit additional that you presented a very nice piece of work, very well-written text. As introduced by your main supervisor, you presented good publication records, already 2 first-order publications in international journals. You contributed to a lot of papers in conference proceedings, and you co-authored other publications as well. So that is at least very, very good to come to the day of today. And as you could see, I even went down to get my jacket to give it a little bit more formal in these horrifying times, I should say, having your defense online only. I think I'm also supposed to challenge you a little bit here on questions, on ideas that popped up during the defense and during writing my report. And I would like, I go back now to my report as well, to online presentation as well, which was a very nice summary of your work, by the way. So I would like to discuss a little bit with you if I have the time. I'm now looking to the chairman. I don't know how much time you can give me to discuss in a bit more, a free way, your opinions, ideas on the work that you presented. You might know, your supervisor, professor, in the meantime, rector, Miroslav, know that I'm an addict of optimal control theory and Pontryagin minimum principle. Unfortunately, I don't have much time left to dig into these things. So I read it with pleasure. Now, my point is that the Pontryagin minimum principle gets applicable as long as the number of equations is limited, as long as the complexity of nonlinearities keep sufficiently limited. And you have been working with respect to this on reduced complexity models with a rather limited number of equations. What is your feeling now, looking back? How complex could your models be to be able still to apply optimal control theory? I know a bit of the answers in the field of bioreactor models, but what's your experience here? I imagine that you started with more complex models and that you had to reduce to make the theory applicable. Could you comment a little bit on that experience?
Yes, sure. Thank you. Thank you for the question. So yes, using this principle, we are limited with the model that we use. So for example, in the second configuration that I'm using, batch die filtration with partial recycle, it has, for at least for a 2-component system, we have 5 differential equations.
Yeah.
And they are, in the end, the objective Hamiltonian function is not affine in one of those control inputs. So we were not able to proceed further to achieve our solution, and we had to move towards numerical optimization. Similarly, when it comes to batch die filtration, it's plain batch die filtration. In that case too, right now we just had the time to implement for simple cases. I mean, the basic cases, not the simple. That is when the rejection of lactose is complete rejection. And for the other component that is solved, it's complete permeability. So it's completely allowed to pass. But of course, the complexity arises when we have more than 2 components. They have this rejection dependent on concentrations. So in that cases, the complexity keeps on increasing, and it would be interesting to find out what we can achieve analytically in those cases.
No. But as you did not go into further detail yet, you had other things to do, of course.
We actually did some research I co-authored with my colleague, which was with fouling, and we did only one where one of the components rejection was dependent on concentration.
Yeah.
So still 2-component system, but one of them's rejection was concentration dependent and not a constant number.
Yeah. And you might then notice that even if the system gets a bit more complex, that you can still deduce a law for the singular part, the singular arc in the optimal control. It gets more tricky, difficult then to find an optimal switching time on the basis of states of the process and not just in open loop. So you obtain, again, a very famous solution. We call it the turnpike or the highway problem. You approach the highway as soon as possible. You stay as long as possible on the highway, minimum time, so you can drive at perfect speed on the singular arc. And then you take the last possible exit, and you nicely confirm this in your results. Now, how robust is this kind of strategy in terms of a real setting? You have then moved into the application to the lab scale systems available in the lab. Even if you could not do all of this in detail, we assume a simplified model. We assume perfect knowledge of the model. In the derivation of the optimal control, we assume perfect measurements. How robust, literally, are these statements, hypotheses, with respect to a real-life implementation? What's your experience and feeling there?
Yes, so as I was discussing, a very long part of time was taken just to set up for the experiments.
Yeah.
So as you said, the model and the measurement of our states is very, very important for this implementation. So yes, a lot of experiments were done prior to these experiments. to confirm all of this, to see the membrane's parameters, its properties to these specific, for example, components, that is lactose and salt. So yes, if we want to implement this, there has to be some prior experiments and research done to see if yes, for these components, for this specific membrane, is this feasible or not? Are we able to, for example, for some models, for permeate models, the switching curve or the optimal switching concentration is very, very high, and it's not achievable on the plant because plant has a specific tank volume. We cannot increase it. So yes, these all things need to be considered before starting the optimal strategy real experiment.
I like that you say the tank has a specific volume. I forgot, honestly, my copy, the hard copy of the book is in my office and it's in lockdown. I only asked for the PDF, but I have, of course, the questions here in front of me. What was the exact volume of the tank in the lab setup?
It's
roughly speaking,
yes, between 3 and 30 liters.
Yeah, so that is still a bit far from maybe a real setup, but you point to an interesting thing. Could you use your work also to design a plant? If you consider the optimization problem, it would then be, of course, a degree of freedom of a completely different nature. It's not an alpha that is continuously manipulated, but could you include in your optimization results, for instance, the volume of the reactor? And would that then lead to different insights, you think, or?
Yes, it might. It might actually, if our optimal control theory gives us a switching concentration which is much higher, then increasing the volume, for example, or using another degree, of volume, can help us in getting better results.
Yeah. Now, and then you did some manual. I know I need to go back to my report a bit deeper on. You did indeed consider one of our favorites in the team as well, multi-objective optimization. And you adjusted the weights, if I understood your text correctly, the individual weights you have been varying in a manual way. Correct, eh? So yes. Based on this, could you give already guidelines or could you automate this process of coming to a set of Pareto optimal solutions?
Yes. So first, in simulation, we use these estimated models, and then we kind of make a Pareto front between both the opposing objectives. And then we kind of give it a cost. For example, the processing time, we give some cost based on the current engineering principles, and also to the diluent, pure water, we give some cost if these are the objectives. And then in the Pareto front, we have many possibilities of these weights. And we see then, okay, these are the interesting ones. These are the interesting cases. And then we use the on the plant, yes.
Yeah. Well, you might know there are automated methods to design or to compute the full Pareto front, but of course that was already a bit also towards the future of your work. When you say multiple objectives and there is a time optimality, it also points to a question of my colleague, Professor Kozakova, if I say that correctly. There is an economic cost, there is energy cost, there is other costs. How do you compare these costs in a multi-objective setting, and is this then realistic? Or do you think your solution, the final solutions, are they very sensitive to your appreciation of a cost of minimal time and energy cost, other costs that you consider? Is it possible that these solutions completely get different when we assign different prices to these? We are used, of course, as mathematicians to a cost in terms of systems theory. In economic MPC, you also work on this in your team. We talk about real costs. How do we harmonize all of this? Do you have any ideas on this?
Yes. If these costs are varying, yes, it's totally dependent on the cost of weighting functions or weighing objective. So if we take them equally, so we can only assume the price. Yeah, we cannot say that in this industry, when they're doing membrane separation, they are using or paying this much of cost for the water, or for the pumping of the fluids, or for the time, manual work and everything. So yes, it depends on from place to place, cost to cost, and it can change. Yes. but the analytical solution, for example, it stays the same. It's a global solution. So based on the cost, of course, for the multi-objective, we might need to change the weights, but in order to minimize the cost, this optimal alpha or the diluent ratio should stay the same based on the model. Yes.
Yeah. Now, I can't call you Ayush, right? How far are you from? So you did mathematical work, you did analytical work, manipulating formulas, optimal control, Pontryagin. Part of this you could implement in practice, test some strategies out on the lab setup available at your site, which is a nice achievement, very nice achievement. I like that both aspects are represented in a thesis. Now, what is next? How far do you think we are from going to full-scale, optimally operated membrane processes? Is that still another PhD thesis, or with your work we can do it in 1 year? What is missing before we go full-scale? What do you think?
One of the first steps that is we would like to, or if somebody would like to do, is these permeate models we estimated before the experiment.
Yeah.
One of the things that can do it better, our optimal implementation, is that we estimate them while doing the optimal strategy experiment. So as we are implementing our optimal strategy, at the same time we are getting the full permit for a data, and we are estimating it online. That could give better solution and more kind of globally implementable solution.
Yeah.
Because there can be a model mismatch if we go to a higher level of plant. This is one of the things. Yes.
What could be the nature of that model mismatch, do you think? Going from small scale, pilot scale, 10 liters, say, average, to a full scale, where could the model mismatch come from?
The model mismatch can come from, first of all, the sensors.
Yeah.
Yeah. As I said, we don't have sensors for measuring concentration. So we have to find some other techniques or ways to measure the concentrations.
Yeah.
So we need, for example, model for that. So that model can lead to a model mismatch in this one.
Yeah.
Then we have those temperature measurements, temperature controllers. So for example, the lactose solubility, it is highly dependent on temperature.
Yeah.
So for example, if temperature is low and the concentration is very high, it will not dissolve. And it will stay at the bottom of the tank. And if the tank is very, very huge or big, we have more possibility of this lactose settling down at the bottom. This will falsely increase the permeate flow rate, but it should not, because there's less concentration of lactose.
You reach now a point that intrigues me, because we work on bioreactors and you work now on membrane processes. Mixing or assuming that the contents of that big bioreactor for our problems is homogeneous is an issue. And you mentioned, we could have some sedimentation in the tank and so on. How important is that three-dimensional model? Do we need to take in the models for the full-scale plant? Do we need to take spatial heterogeneity into account, and then we end up with partial differential equations where a concentration in the tank depends also on its position in the tank? Or is that not needed in your applications? What do you think?
It will again depend on the size of the tank. For example, in the tank we have an agitator in the tank, and it was enough.
You mean the one in the lab?
Yes.
Yeah, okay. Yeah, this I can see. Yeah.
We had an agitator there, and the agitator
you
can
agitate. Yeah, okay.
Yes, exactly. We agitate the solution, so it is homogeneous in each part of the tank. But yeah, that again depends on the other plant that we might get, or we are discussing about. If it's big enough, there is no agitation inside, then yes, we will have to think about something of higher level to
and I want
include
to
that in
challenge
our
you
model.
to do Pontryagin minimum principle on PDEs, on partial differential equations. That's another story, but that's for another PhD maybe. Now, I understood from the introduction from colleague Michal, or maybe from colleague Miro, that you're lost for science and that you joined IBM.
Yes.
Or something. Good for you, congratulations. But I still have a question. As we work in the chemical, environmental, food area, when we want to do a project with industry, and now you are at that side, it's always an issue, especially when you work in optimization of processes, in optimal control and so on, how to convince the management that this makes sense. Now, with your experience, how would you convince a full-scale operator of a separation process that your technology, that your methods, that your techniques could lead to an improvement or an economy and so on? Have you now convincing arguments? Look, we have now done this, we validated on lab scale, now you need to pay us to implement it at full scale. Nice. But the management will immediately ask, okay, what is the return on investment? What will we gain? As my colleague said, time minimization is one thing, energy costs and so on. How convincing can you be at this moment to sell it to somebody, to pay you to implement it to the full scale? That's what we need in the end. Or do we need more work at this moment at academic level?
I would say for this particular, for example, lactose and salt separation, which is, so prior to this, when in my master thesis, I was doing this work. So I was using, so we had whey, which is coming from cheese industry, as a solution which has microorganisms, fats, proteins, like carbohydrate and sugar and everything. So we separated each and every component, and in the end we had lactose separated from the salt, and that we use for making some kind of galacto-oligosaccharides. So these are good for our prebiotic properties.
Yeah.
So if it's particularly this kind of case, and there are not multi-components, yeah. So if directly we are given whey, yeah, which has, I don't know, hundreds of components, yeah, then our theory might need more work.
Okay.
But if we have, for example, simple two-component solution, then yes, it should be doable. After some experiments and research, it will of course take some time with the new plant, but it is doable, yes.
Yeah. Now you mentioned there the separation of two components. What do you think is most important? I know it for the pharmaceutical industry, they want to stay as within specs, and that's their absolute requirement. We can claim we can improve your production, but we want to be within specs. Do you think that for this area of applications, staying within the specs here, then the separation efficiency is more important than gaining a bit of energy or a lot of energy? How would they see this? How would they balance this?
Well, for example,
I try to challenge you a bit to the broader picture. You can see that.
Yes, obviously, the constraints on the states, they are very important.
Yeah.
So in industry, of course, there are specific regulations that, of course, the concentration or mass of this specific component should not be more than this or less than this. Within this range it should be, or exactly this number. Yes, with our, as I said, with our current application, we were able to reach those concentrations. So we had an objective that from this initial concentration, we want to reach this specific final concentration. So with this optimal strategy, we were able to reach that final concentration. And for example, we had a constraint on the volume. So in one of the cases, we had to apply suboptimal strategy. So the switching concentration was more than what we could achieve. So we did the maximum we could, staying within the constraint, and still we achieved some better results. In way of cost, we reduce the cost.
Yeah. Okay, thank you very much, Ayush. I think I better, or I can safely conclude here, and I can reconfirm what I wrote in my assessment as your official opponent. First of all, I wished I could oppose you in real life, but okay, that is not possible now. But I want to reconfirm that your submitted manuscript, without any doubt, complies with all the conditions set for a defense, that your presentation and the way we had this little discussion, interesting chat, is more than convincing to award you the degree after we will have our deliberation pretty soon after everybody has asked his questions. But already on my behalf, thanks for the interesting chat and best of luck in your new job, of course. And I hope somebody else in the team will follow up on the interesting work that you have been doing.
Thank you.
Thank you.
Thanks a lot. Thanks a lot. Thank you.
Thank you very much, Professor Jantanimpe. Now I would like to open the general discussion and invite the members of the committee to ask their questions. So whoever wants to start, just please unmute your microphone and ask your questions.
Can I start?
Sure. Sure, go ahead.
I have one question connecting fouling. In audio treatment, you suppose constant mass transfer coefficient. But in reality, for example, such systems like these proteins or this biomass, this mass transfer coefficient is not constant, it is time dependent. And this question is not much discussed in your work. How do you assume that can influence your modeling? Is it possible to include this time dependence, for example, mass transfer coefficient to your models?
Hello, thank you. Thank you for the question. Yes, it is true that we are not including fouling directly into the optimal strategy, which we implemented on the plant. But the experiments, initially when we did experiments, we figured out the fouling part experimentally, that how much is it affecting during our experiment run. And we, after many experiments, we figured out that only initially for a certain time, the fouling is prominent. So the flux or the permeate flow reduces or decreases quite fast or with a big gradient initially. So for that part, we run the experiment in complete recirculation. So the permeate is not allowed to leave the system. Everything returns back to the tank. And once this fouling is somehow made constant or it's made less prominent, we start the experiment. So basically, we reduce the fouling mechanism initially by not starting the experiment, but just running the plant so that membrane can settle down to a certain amount of fouling. But yes, you're right. In future, if there are more molecules, proteins, and fats, this fouling is even more prominent, and it should be included in the further research in the optimal control implementation.
You know, you mentioned that initial time part, that it comes to some steady flux, but that steady flux is also time dependent. That steady flux, it depends on time and sometimes quite importantly.
Yes,
so
yes.
You never reach in systems with proteins real steady flux. That's the point. I don't speak about that initial period, time period.
Yes. In future, yes.
All these cleaning procedures to remove fouling are
yes.
very important in the industry. So in the time sequence, these cleaning periods are quite important.
Yes, we were cleaning after each and every experiment. So we had that chemical cleaning, we were cleaning with an acid, then with a base, then with pure water, with cycles of this process after each experiment.
Okay, that concerns your measurements, but in reality, you can operate a plant till some steady flux is reasonably high. Then you have to clean, and it needs some time, some standby modules, for example, to be used for application and then clean. And so the time sequence of using modules and plant is quite important for economy, of course.
Yes, yes, yes.
Thank you.
Thank you, thank you, thank you.
Okay, who wants to go next? Professor Bakushova, probably.
Yes, I can. So I will have a question concerning the P&I diagram in your presentation. It was the slide number 8, as I can see it in the presentation. And so my question is, you explained the role of two controllers, pressure controller and the temperature controller. But I can see another controller in this scheme. It is the controller FFC. So
Yes.
Could you explain the role of this controller in the process?
Yes, this is the feed flow controller, and this is the actually controller we use to implement our optimal alpha using our PC or MATLAB to the plant. So this is the feed flow controller, which is in the MATLAB. We just need to use the HMI and implement it.
Because when I saw the FFC there, I thought that is the flow fraction control. So it is my question, is the flow fraction controlled or only flow control?
It's only flow controller, yes.
Okay, thank you very much. And I will have also the other question. So you use optimal control for your membrane separation. Do you have any knowledge about implementation of another advanced control approaches to control of such a process? Maybe any experimental studies or simulation studies in the literature?
Simulation studies, yes, we did with
and what advanced control strategies were applied to membrane separation?
To the plant, we only implemented this particular strategy. When it comes to simulation, we also did in batch distillation.
But I saw the other authors. So when you went through the literature, did you find any applications of other advanced control strategies? Because my questions follows from the discussion with the and because you mentioned the process model mismatch.
Yes.
So is this problem solved in the literature also for membrane separation?
Actually, I was not able to find any research-related implementation of these strategies on the membrane plant. So actually, in industry, they just use these basic modes. They don't use any kind of optimal or higher level control strategy to minimize the cost or to do this industrial work.
Oh, thank you for your answers.
Thank you.
Thank you. Who wants to go next? Professor Marcos?
Dr. Sharma, you use your optimization strategy for nanofiltration process.
Yes.
Means driving is difference of pressures on the side of membrane.
Yes.
Can you imagine your strategy or your models to use for other membrane processes?
Yes.
For its concentration gradient.
So this, in theory, this strategy is applicable globally or universally for any membrane type because we keep the pressure constant based on the membrane. So in this case, we were using nanofilter. So we were keeping that using that pressure controller, the pressure in the range which is applicable for nanofilter specifically. So if we, for example, use ultrafilter for separating protein and sugar, then we will set up our desired value of the pressure according to that specific membrane. But the theory, it stays the same for each type of membrane.
Could you repeat? I didn't hear anything.
Yeah, I'm not on mute. Okay.
That's a problem with connection. Okay, don't do it. My another question is: your system was or batch or semi-batch?
Batch.
And can you imagine it to apply it for continuous process? For example, per evaporation, per tractions?
Actually, for that, the model will change and everything will have to be started from scratch. So the model and whatever, this is a model dependent control strategy, and currently the model we have is only for batch. So if it goes to continuous, it will be started again from scratch. using
Okay.
the continuous model.
Okay, thank you.
Thank you. Thank you.
Thank you. So now we can give the word to somebody else, Professor Mészáros.
Hello. So Ayush should have been tired by now, but therefore I would start with optimistic sentences and judgment. I really do respect the work what Ayush Sharma has done and has presented.
Thank you. Thank you.
Because of a lot of things, it was a very good attempt to combine practical and theoretical aspects, and I think he has done it in a quite successful way. Not to say that batch processes themselves, they are not too user-friendly for process control implementation. My suggestion or question is, you have studied this process of membrane process. Do you think that such a process could be run maybe in a different regime, not only batch regime, but let's say fed batch or even continuous mode, this at least in laboratory conditions? And this is my question for just to think it over or to say something about that. The other thing what I do appreciate is the compromise you try to find between the different technological expectations, like water consumption minimization, time minimization, power minimization. I don't think that you have come to complete solution from this point of view, because I think technological points are much more important, and maybe you have not studied them so much, because it depends on access to the water, on access to electricity, and a lot of other things what you have not you were not what you were not able to take into consideration. But anyway, I think it was a good thing to try to do the best compromise within this. So also your point of view on this. And what my last thing, what I would like to add, that you mentioned the method of orthogonal collocation. I have not catch whether you have used it, because this is for solution of partial differential equations, and I haven't seen from your among your results which would refer to variables depending on two variables, time and let's say position. So it was then used this method for what, and where were the results of that? So that's all.
Okay, so the first question was regarding continuous and feed and bleed.
Just let's say
yes, they are used in industry for membrane separation. These other modes, so fed bed and feed and bleed and continuous. But the membrane plant that we have in our laboratory, it was designed for doing batch membrane processes. And as we move to other types of processing modes, as I said, our model will change, and then we will have to do some alterations in our membrane plant.
I wanted to know your opinion. It is not that I'm not blaming you that you have not done it. I just your opinion, whether it would help from the point of model mismatch diminishing or model mismatch reduction or not. But okay, I think it is enough to this. So please to other things what I said.
Okay, and the second point. Okay, I remember the last one now, the orthogonal collocation one.
Yeah.
Yeah, so the orthogonal collocation, so the simulation results that we have from the second part, that is batch die filtration with partial recycle. So we use the Dyno toolbox, which uses orthogonal collocation method to discretize both the states and the control input. So we use this to find the optimal solution in simulation. So
yeah,
yes,
it's
so
only
this is how,
only in simulation.
yes,
And
yes.
not in the laboratory.
No, only in
No.
simulation. Yes.
Okay, and the other thing that was about the compromise between between the different assumptions, but I don't think that we can solve it now. Just I wanted to point out that this is also a question which probably there is more space for the future to analyze. Thank you very much. Thank you.
Thank you.
Thank you for your question, Professor Meszaros. Now, Professor Petras.
Actually, I don't have any question. I just want to say that I came briefly through the thesis which Michal sent us. I could see presentation, and I would like to say that I like it. It's very interesting work.
Thank you.
And it's actually supported by papers in high quality journal. So congratulations, good work.
Thank you.
Thank you. If I may, I would like to ask one technical question. In your presentation, you mentioned the parameter estimation problem. So my question is, how numerically did you solve this parameter estimation?
So we use MATLAB to solve the problem. We used the sequential algorithm. We use interior point algorithm to solve the problem, and yeah.
Because the parameter estimation problem is non-linear. So do you have a guarantee that you have arrived at the global optimum of this parameter estimation?
No, it was numerically, so it's probably local optimum. It's not global optimum.
But you didn't check other options like starting from different initial conditions and seeing if you arrive at the same solution?
Yes, we did many other experiments, and so with different initial points. And yes, the model was more or less fitting those data too.
Okay, thank you. That answers my question.
Thank you.
Is there anybody else who would like to ask maybe more questions? I don't see anybody turning their microphones on, so I take it as for no. So with this, I would like to close the first part of the public defense. What will happen now is that the YouTube stream will go on, but the committee will now go for their deliberations. So they will temporarily leave this meeting and they will join a private meeting for deliberations and voting. Okay, so I would like to ask both Ayush as well as the general audience to stay connected. After some time, the committee will come back and announce their decision. So see you in a few minutes. So Jan, Ivo, and Alajos, we should disconnect from this meeting, and I have sent you a link for a second Google Meet meeting. So please disconnect from this one and connect to the other one.
Okay, we will be ready in a few moments.
Okay.
So how did you enjoy your defense?
Yeah. I'm nervous a bit.
It seems that everybody's back in this meeting. So we will continue with the public part. Mr. Sharma, the committee has deliberated, and I'm glad to announce that the committee has voted for the approval of you passing the PhD exam. And if I'm not mistaken, by this point, you are being awarded the title of Philosophy Doctor. Professor Bakošová, please correct me if that's not correct.
It is correct.
It is correct, yes. So congratulations to this fine achievement. The committee was really satisfied with your immediate performance, also with the quality of your thesis and the quality of your publication record. So a virtual congratulations to you. I would like to thank very much both to you as well as to the committee members who have done this online defense for the very first time. I'm really glad that everything went smoothly. I see Professor Van Impe waving with his champagne. Now, what I would call brave would be to open it and spray it all over the camera, but that would probably not going to
Leave
happen.
it. No.
So, but yes, certainly Ayush deserves his acclamation here. So that's all from my side. Thank you again for joining and for taking part in this online defense.
So I would like to congratulate Ayush. So Ayush, congratulations, and I wish you all the best in the whole your life. Yeah.
Thank you.
Yeah.
Thank you very much.
And let us join the same to congratulate to you and wishing a good success in the future, both professional and personal life.
Thank you. Thank you. Thank you.
Congratulations, Ayush, and I really hope I will not open the bottle, that I really hope that I will have the chance to drink it together with you and Miro, of course, once I visit Bratislava at some point in the future.
Thank you. Thanks a lot.
I also congratulate.
Congratulations.
Thank you.
Ayush.
Thank you, sir. Thank you.
Oh, also, congratulations, and I wish you all the best and nothing positive. It is the wish for today.
Thank you. Thank you.
Yeah.
Okay, Ayush, you are in the
Bye-bye.
next office, so I will go to you and speak personally to you.
Thank you. Thank you, sir.
Yeah.
Okay,
Thank you.
bye-bye.
Bye-bye.
Okay, bye-bye. Thank you very much for
Bye-bye.
joining.
Ahojte.
Ahoj.
And enjoy.
So,
Bye.
OK. Ďakujeme, Ivo, veľmi pekne.
čo povieš, Ivo? Čo povieš? Aké to bolo?
Páči sa mi to.
Bolo to také kostrbaté, ale myslím, že sme to zvládli.
Mňa zaujímalo hlavne ten software na tajné hlasovanie.